So here we'll be focusing on these few proofs, the elementary consequences of adding vectors, and also when you are having scalars. So I'll be showing you how to prove this. So we have got, so I was still here, we have got the elementary consequences of adding vectors. So I've got three proofs. You have your additive identity, additive inverse, and cancellation law. And we also have these ones, the one for scalar multiplication. So we have four of them. So you should be able to prove them before the test. So let me just do some of them here. I'm going to start with the ones for addition. Addition of vectors proofs. I'm gonna start with the additive identity. So here we're going to say, so the proof says when you have u plus v, it will be equal to u, and then this implies that v is equal to 0 for u v being an element of a vector space. So now let's do the proof. So I'm going to let 0 be an additive identity of, of the vector space v. Then we suppose, or we can say assume, 0 prime is an additive identity entity of v. Then this will imply that u plus 0 prime will be equal to u, and it will be equal to 0 prime plus u for all u element of v. Now 0 prime, we can say that it will be equal to 0 prime plus 0. Reason, we say the 0 prime is an additive, we say it's an additive identity. So meaning that whenever you add it with 0, you will still get that identity 0 prime. Then we can now apply the property of additive inverse and replace 0 with u plus negative u. So always you must write a reason when you are doing this. Then you will say by the additive inverse. And this will be 0 prime plus u. If you apply the associative property, you realize that you will have this, and this will be equal to 0 plus negative u. It's just negative. So we've managed to show that this should have given us, let me fix this part. When you add this, you will get u plus negative, and this will give us 0. So now we can now say we have proved there. So we can see that 0 prime is equal to 0. So this means that we have managed to prove the uniqueness of additive identity. So this is a proof of showing that whenever you add a 0 to a vector, you'll get that vector, and that 0 is a unique element. So you can have a 0 vector being 0, 0, or you can have another one 0, 0, 0. You see that? That's what we are actually proving. And then we go to the second one, the additive. The one for additive inverse. So this says that if u plus v is equal to 0, then v must be equal to negative for all uv being an element of v. So we can say that negative u. So I'm going to say first say suppose or assume u is an element of v, and it has two additive inverses. Negative u and negative u prime. Now, negative u prime will be equal to negative u prime plus 0, because 0 is an additive identity. Then we can now say negative u prime plus, then we can change 0 to be this. This is true. Then by the additive inverse, we here should write by the additive inverse property. Then this will be negative u plus, if I apply the associative, plus u plus negative u, this will be 0 plus negative. It's just equal to negative u. So we've managed to show that negative u prime is equal to that. So this is the uniqueness of additive inverse. The first one was uniqueness of additive identity. Proven. And we can come to the last one, which is the cancellation law. So we can, let me see something here. Okay, so it states that whenever you have u plus w being equal to v plus w, then u will be equal to v. Even by looking at it, we can see that that was cancelled. So the proof, we can say let u v w be an element of v such that u plus w is equal to v plus w. Then u plus w is equal to v plus w. U plus w plus negative w is equal to v plus w plus negative w. So what did we do here? We just added this negative w. So the reason we say the additive inverse of w exists, we just added. So this is what we call cancel. We can say by cancellation law. By cancellation law, we know that if I take this to the right, it was going to give me 0. We're going to get negative w plus w. Then we'll now go on. This will give us u plus Then we apply the associative property. So you write your reason on the step, say associative property. Then this will be u plus 0, v plus 0, the u is equal to v. So we're done. Then we come to the one for properties of scalar multiplication. So we're going to say, so it's either you prove, they ask you to prove that you have this, or alpha u 0, then if alpha v is equal to 0, then either alpha is 0 or v is 0. D negative 1, v is equal to negative. So I'm going to start with A. You must prove that 0u is equal to 0 for all u values being an element of the vector space. So we can say let 0 be an element of the field F, or you can even say 0 be an element of the vector space, is still fine. Then we know that 0 is equal to 0 plus 0, right? We know that this is true. Then we can now say if I multiply both sides by u, just introduce it, then this was going to be 0u plus 0u. Then now want to apply, so this is by distribution property. Now I want us to add, we're going to add negative 0u both sides. So this will be equal to, so you'll say by cancellation law, this will be 0, then this will be equal to 0u plus, then we group this will be 0. So managed to show that 0 is equal to 0u. Because you know when you add these two, you'll just add 0. So we're done with the first one. And then number B, they said show that alpha 0 is equal to 0. Okay, I'm going to skip B for now. Let's start with C. They say if alpha v is 0, then either alpha is 0 or v 0. Then either, and this one they like asking it to take note of it in the test or even the exam. Then either alpha is 0 or v is 0. So we're going to suppose alpha is not equal to 0. So this implies that 1 over alpha, we can say it exists for all alpha being an element of the vector space. Now, if I say v is equal to 1v, I wouldn't be wrong. This is true. Then I can come here where there is 1 who can replace by this. Then you'll just get 1. You'll just get 1 over alpha v. We can write this by axiom 8, axiom SM8, or let me just say by the what distribution property, which is SM8. Then now we can say this is equal to 0. Why is this equal to 0? You must first replace this with 0. from, since we said suppose alpha v, so this must be the first statement you write. We're supposed to say suppose alpha v is equal to 0. What's happening? We're supposed to say suppose alpha is not equal to 0 and alpha v is equal to 0. We're supposed to suppose that. So this is our hypothesis. So you can say from the assumption or hypothesis. You can say from assumption. And now this means that v is equal to 0. Then I think now we can go to tutorial 2. Can go to tutorial 2. So you'll try to check the ones that I didn't do. Or you can prove that alpha, if alpha v, if you have alpha 0, it's equal to, then will be equal to 0, then d negative 1 v equal to negative b. I think we can still show this. Let me try to do at least one of these because they can bring in. So let's try to show letter D. I want to prove this one. So we're going to say let D be any vector in V, and you let 1 be an additive, be a multiplicative identity, such that 1 is an element of the vector field. So now you can say V plus negative 1V. We know this will be 1 plus, this will be equal to 1 plus negative 1 times V, right? So since V is equal to 1V by the identity property, this will imply that V, where there is V, we can write 1V plus negative 1V. Then this will now imply that if I take out V as a constant, you'll have 1 plus negative 1. And this will just give us 0, and this will just be, and this now implies that this will be equal to 0. Anything times 0 is equal to 0. So I've managed to show this. It's equal to 0. So we're trying to show that, remember, we're trying to show that negative 1V will be equal to negative V. So we also know that 0V is equal to 0. We know this is true, or 0, let me just say 0U is equal to 0 for any vector. So now when you have V plus negative 1V, it's equal to 0. We already found that this is equal to 0V, this is equal to 0. Yeah, you guys will check how you can write it more simpler. Then we also have letter B. Let me also show you how to do letter B. You have alpha 0 equal to 0. You can say let 0 equal to 0 plus 0, and you introduce alpha. Then this will be alpha 0 is equal to alpha 0 plus alpha 0. Then we can add negative alpha 0 both sides. And this will give us 0. Then this part you apply the associative property. You'll have negative alpha 0 plus alpha 0 plus alpha 0. So you realize that this will give us 0 plus alpha 0, 0. And this will just be x. So the second one is quite simple. Then try to redo that if you don't get it. And let's check what we're expected to know on tutorial 2. So we're talking about the subspace of a vector. They say determine if W is a subspace of a vector space V. So what's a vector? That's a subspace. So this is the definition, but I want us to write it in our own way. Define what is a subspace of a vector. And also the conditions that are related. So you will say it's a non-empty subset of a vector space that is itself a vector space under the same vector addition and vector and scalar multiplication. So, and these axioms, the following axioms must hold. Must hold. So the first one is that we're going to say let W be a subspace, be a subset of a vector space V. Then W is a subspace of V if and only if the following axioms hold, if and only if it contains the zero vector, when zero is an element of W of that set. Remember, W is a set. 2, closed if you have got closed under vector addition. If your vector is closed under vector addition, where UV is an element of W, then 2 plus V is an element of W. The number 3, it must be closed under scalar multiplication. U is an element of W, and if C is the element of your field, then you can see Cu is an element of W. So if these three conditions hold, then we can see that it's a subspace. So let's come to your tutorial here. Tutorial 2. So let me first start with my own example to explain what's happening before that. Number one, suppose yw is equal to xy. It's an element of this such that y is equal to 2x. We can see that if I let vector u to be 0, 0, we can see that this is an element of R2 sine, because even if you check, if you let x to be 0, y will be 0. So the first condition holds. We can say the 0 vector 0, 0 is an element of your set. Then we want to now check the second condition that says the sum of two vectors must be in the set of W. We want to check this one. The second condition here, which is this one. So we can see that I want us to create, we know that if I let u to be, suppose we let it to be 1 and 2, and then we let w to be 2 and 3. Both of these are an element of R2. We can see that if I perform the addition of these two vectors, you'll just get 3 and 5. This is an element of R2. And suppose I take vector, I want to check, let's also check okay, this, we are not proving a vector space, remember that. So this is an element. If we check 3 and 5 is still an element in W. Why? Because this is an element of two variables, x and y. Then the last one, if you multiply vector u with any vector, you'll get what? C to C. So you see that if this is x and y, the condition y is equal to 2x is going to hold, because we're having what? We're having our y as 2, and then our x, suppose we don't know, you'll get x is equal to 1. You see ne? So yeah, so anyway, here we can just say that Cu is an element of the subset W. So you can say W is a subspace of R2. Number one, now come here on tutorial 2. They are saying W is given by ABC being an element of R3 and V is equal to R3. So I might not do all of them so that the recording is not too long, guys. Then here we're gonna say start with number A. Want to check if you are having a subspace. Okay. So why given this? So you're given that A is equal to 2B is equal to 3C. I can say, let's check for the 0 vector. We can say let A equal to 0, B equal to 0, and C is equal to 0. Then we can see that you'll have this 3 times 0 from this condition there. So we just have 0 is equal to 0 equal to 0, right? So we can clearly see that 000 is indeed an element of R3. So the first condition holds. Then we check for closure under addition. So we can say let U equal to A1, B1, C1, and equal to A2, B2, C2 be an element of W. So I want us to check this one. If we do U plus V, we add these two vectors. We will get A1 plus A2, B1 plus B2, C1 plus C2. So we want to check this condition here, if it's satisfied. So A1 plus A2 will be equal to 2. Remember, we're having A is equal to 2B is equal to 3C as our condition there in the element of real numbers. This was our condition. So you'll multiply with B with 2. Right? And then you'll also multiply C, vector C. We're multiplying all of this. We're applying that condition here. So you will have this. Then you are now having A1 plus A2 is equal to 2B1 plus 2B2. And this is the same as 2B1 plus B2. And also C1 plus C2. This is the same as, remember when we multiply that this one with 3, you'll get 3C1 plus 3C2. So we're having this. So this is the same as having 3C1 plus 3C2, right? If I take out 3, you'll just have C1 plus C2. So we can clearly see that U plus V is an element of the subspace of W. Then we can check for closure under scalar multiplication. So we can say let alpha be an element of real numbers, and U, we know that is A1, B1, C1. It's an element of W. So we can say K, we can say alpha U will equal to alpha, we multiply vector U. So we can see that you'll just have this. Since our condition states this, so multiplying by K give by alpha give us alpha A1, 2 alpha B1, multiplying that, and also give us 3 alpha C1. So we can say alpha U is an element of the subset W. So that's how you'll do number 1. Letter B. And let me also take letter C. and V is equal to F3. So and that's now to check letter B and letter C. So I'm going to start with B. So I want to show that W is a subspace of R3. We can start with the first condition, the zero vector. So we can see I have 0 cube. Let's first say that 0 be an element of W. This is the first thing you must write in there. Then you can see that you'll have 0 cube is equal to 0 cube from this condition here. Then this implies that you have 0, 0, 0 be an element of W. Then check for closure under addition. If I let U to be A1, V1, A1, and I let V to be like that. Ne? Remember, if you are having a condition that A cube is equal to C cube, if you cube both sides, you'll realize that A is equal to C. That's why now on my vector here, on my vector U and vector V, A and C are equal. If you check A and C are equal. A and C are equal. So now, want to check the addition of U plus V. So it means you'll be adding this. A2. And this will give us A1 plus A2 plus A2, A1 plus A2. And you can see that this is actually going to be an element of W. Since this is equal to, we're getting that this is equal to this. So try to be observant, guys. We can see that A1 plus A2 is equal to A1 plus A2. So this is like A is equal to C. So now we can say that this is an element of W. Then you'll just write this as derivative since this is equal to that. Then we can check for closure under scale. You'll say KU will be equal to K A1 P1 A1. This was our U, and you'll get K A1 K P1 K A1. So you can see that K, since K A1 is equal to K A1, therefore KU is an element of W. Therefore W is a subspace of R3. Then we come to this one. We know that for a vector, this was C. We're going to check for the zero vector. We'll say let zero be an element of W. Now, suppose our vector, obviously, if this is an element of R3, then this means that we want to apply that condition. It means that 0 will be equal to 0 plus 0 plus 1. And this implies that 0 is equal to 1. So this is false. This condition fails. Remember, one day it's fixed. But since this is false, you will say 0 is not an element of W. So the first condition fails. You don't have to go to the second one, but you can continue. Then you can check for vector addition. So we can say let U to be equal to 1, 2, 3. And B to be 2, 3, 4. So U plus B give us so actually here we should give a this is not correct. We should give a vector that will satisfy this condition. A plus B plus 1 is equal to C. So must give such a counter example. So let's try to use our counter by counter example. You can let U to be 0, 0, 1 so that this can work, and B, let's say we say negative 1, 0, 1. We know that this will be negative 1 plus 0 plus 1. Oh, this will give us 0. I wanted the one that, oh, here we can say 2 on the second position. You can say this is 2. Then plus, this one give us 0. Okay, we'll say negative 1, then 2. Or we can say 0. Ne? We want to get C being equal to plus 1. Okay, yeah, we'll see 1 here. So this will be negative 1 plus negative 1 plus 1 is equal to C, which is 1. Then this will give us 0 plus 1 is equal to 1. Yeah, it's fine. Now you'll perform U plus V. So you add this. So you'll get negative 1, negative 1, 2. So we're going to check now if that condition is met. Our C is now 2. So you'll say negative 1 plus negative 1 plus 1. What do we get? You'll get 0 plus 1. And 2 is not equal to 1. Therefore, U plus V is not an element of W. Therefore, W is not a subspace. And let me just do the last one. We'll continue again on the second recording. I'm going to take letter D. V is equal to M. So I want to show that this vector is a subspace. So this is what you are having. So we can split this vector in this way. 5. We can write it like this. If I take out A, you will have 1020. Then if I take out, so you must be able to see, if I take out A, you'll remain with 1 here. Here you'll remain with 2. Here you'll remain with 0 and 0. So that's how I'm doing this. So I'm creating a basis. Then B, I take out B, you'll have -3, 2, -1, -5. I take out C. So we will be having something like this. Here. We'll be having this. So this shows that W is a span. It's a span of R3. So, but I want us to do it in a simpler way, né? But for now, I can say W is a span of R3. I want us to do it in a much simpler way, because we have to check for the 0 vector and all that. So here we're going to say, if we're not trying to show the span, we can try to say let our 0 vector to be, so this is the first condition. I want to show you in this way that y is to be an element of W. So this one, it can be satisfied, but we're going to check it. We have -5b. So we're going to replace the 0 wherever. So we're letting A, B, C to be 0. So you'll see that this will give us zeros. So 0 is an element of W, the first condition. Then I can let U to be this. A1 minus 3B1 by 2B1 minus 3C1. This is, yeah, minus 5. This is 5. 2A1 B1 minus C1 minus 5B1. And we can let V be this. Now you'll do the addition of A plus of U plus V. So this will give us A1 plus A2 minus 3B1 plus B2 and this will be 2B1 plus B2 minus 5C1 plus C2. Hey, remember this thing is one thing, eh? Then this will give us 2A1 plus A2 minus, when we add this, minus B1 plus B2, then we add C1 and C2. This will be minus. Then we add the last ones, the last row, which is those. We'll have minus 5 B1 plus B2. So we want to check this condition if it's satisfied. If this will be an element of real numbers. So I'm going to say let A3 to be equal to A1 plus A2. And then we let B3 to be equal to B1 plus B2. Ne? Then C3, we let it to be C1 plus C2. So if we do that, our resultant matrix will be A3 minus 3B3, 2B3 minus 5C3, negative 5B3. That will be the result, and this is an element of W. So if we check for the scalar, I'm just gonna write it quickly. I already wrote this. So we're having this matrix. So I'm multiplying with vector U. So our result here will be KA1 minus AK. Then here you'll have 2K KB1 minus KC1. So this is our matrix. We're multiplying matrix U. We know that matrix U was equal to this. So we're just multiplying matrix U with our what? With our constant, which is K. So we can see that if I say let A4 to be KA1, B4 KB1, and C4 to be KC1. This will result as A4 minus, this will give us 3B4. Since we said B4 is KB1, then you will have 2B4 minus 5C4, then 2A4 minus B4 minus C4, and negative 5B4. You'll have this, and this is an element of W. So we can just say KU is an element of W. So the third condition also holds. Therefore, W is a vector space. So